this session is entitled Accelerating Cooperation in the Field of Space Resources. If we want the chance to go further in our exploration of space and the utilization of space resources, it's essential that we enhance the collaboration among the various stakeholders. And this involves, of course, sharing knowledge and resources, leveraging technological advancements to accelerate the progress towards the sustainable and responsible use of space resources. So, another packed session. First up, we have Giorgio Magistrati, who is going to talk about the Argonaut focus on ESA. Now, Giorgio is leading the expert team in Human and Robotic Exploration Directorate in ESA. Please welcome him to the stage.
Good morning. The main reason why I'm here is probably because I have to answer to the question that some of you might have, that is indeed what is that. It has been already introduced by Matthias, my colleague Matthias, and as well by Bertrand, that is Argonaut, but the intention is to provide you more information about the lander, Argonaut lander, and as well also to discuss a bit what is the link between Argonaut and in situ resource utilization. But before doing this, let me also spend a few words about the Terra Nova program. So the ESA Terra Nova program is leading Europe a human journey into the solar system. We have 3 destinations in one single program. We have following the principle of continuity. We want indeed basically to maintain the presence of humans in LEO, but as well we have ambition to have a European on the moon by end of this decade, and we have a vision as well. So the final target is indeed to have a European on Mars in 2040. We are as well inspired, and ESA together with the member state, the participating state, and as well industries, we have started recently activities that is trying to study and to develop a human and crew and a cargo transportation system. It was already presented also by Bertrand. I mean, we are able basically indeed to concentrate, to condense all the different activities that we have proposed and we are implementing now in one single slide. Is a combination of projects that we started in the previous period and we are continuing now. Good example is, for example, the European Service Module, that is a service module of the Orion capsule. But as well, there is also new entries, and one of them is indeed Argonaut. Argonaut is the European lander. Argonaut is the new name of what it was known as a European Large Logistic Lander in the previous period, is able to provide an autonomous access to the whole lunar surface to Europe. The idea is not to have Argonaut as a single mission, but indeed as a sequence of missions, and the cadence of these missions should be one every 2 years. The idea is to make use of European launcher, Ariane 6-4, and it should contribute as well to have the first European astronaut on the moon surface. In more detail, there are 3 different elements that are composing Argonaut. The lander descent element, that is the part that is basically the white part, with the legs and with the engine. This is basically the section of the Argonaut that is essentially a kind of inverted launcher. Is able to land and to deliver to the moon surface something between 1.5 and 1.8 tons of materials, consumable and payload. The idea is to distinguish between the lander, the LDE, and the passenger, and to interpose a payload adapter that will be able to cope with a different type of payloads that we may embark on Argonaut. For example, here what you have an example of a payload. In this case, is a European charging station clearly is just a mock-up. So the idea is to have as a payload infrastructure that is able to provide up to 10 kilowatt during a lunar day to whatever type of payload we may have on the moon surface. There are also additional services that can be provided by Argonaut. So, for example, we can also provide night survival capability, making use of different solutions. In the slide is mentioned the fact that we can use RPS, this is radionuclide radioisotope power system, but as well we can also combine different technology, like, for example, fuel cell system, regenerative fuel cell system. The accuracy, at least for the first set of missions, is in terms of precision landing, is about 50, 100 meters. There will be possibility to improve this accuracy. Also, why not making use of a beacon present on the surface of the moon? And the idea is to develop in such a way that is compatible with a first launch end of this decade. There is also, as well, the idea to think about an evolution of this lander. So we start with 1.5, 1.8 tons, but we can also extend this capability thanks to the fact that there will be an evolution of the launcher itself. In terms of status, where we are now, we have completed the phase EB1. We have 2 parallel contracts with 2 primes in Europe. And we have issued in March of this year the ITT for the phase B2. So, and we will select one single prime that will continue the development. So what you see here is a kind of agnostic model. It's not indeed the design of none of the 2 primes that we have now. It will change, but is basically what has been designed as part of internal study in 2021. Clearly, the ITT that is mentioned in the slide is the ITT for the lander, but we have also to define the first mission of Argonaut. It has been decided, and it has been proposed already 2 years ago, that the first mission will be in full support of the Artemis program. So what we are doing currently, in collaboration with NASA, is to define, finalize mission concept for the mission number 1. We had a technical interchange meeting with NASA early April, and we are expecting to start phase B1 of the Argonaut mission number 1 in early 2024. The idea is to have a main payload, like a utility rover or logistic cargo capability, but this payload will be complemented by secondary or ancillary payloads that could be science or technology demonstrator. Indeed, we have a full portfolio of mission ideas. We have definitely more ideas than budget in Europe. And for example, what is listed here is a set of different scientific missions that are covering biological, scientific goals or exploration goals. And as well, we have a set of missions that are indeed providing infrastructure, like, for example, charging stations or ISO pilot plant. Okay, which is the link between this and this Argonaut and this conference? Well, it's quite obvious. Argonaut will represent an opportunity to deploy and operate on the moon surface techno demo, but as well, basically, main payloads. And last consideration is about the name. I think that Argonaut was as replaced the previous name that was YEL-3. Probably, I don't know if you know, but there are at least 50 different members of the Argonaut Argo crew. So we have different options. So it could be that indeed we will have issues in the development qualification of Argonaut, but definitely we don't have difficulties in finding a name. And each Argonaut mission will have a name of an Argonaut member. It could be, for example, that the first mission will have a name of Jason, that is the commander of the Argo crew, Argo ship. It could be Heracles, that by chance it was indeed a previous name of a precursor of YEL-3. But it could be also that indeed the first name will be Atalanta, because indeed, surprise, surprise, it seems that there is only one female member of the Argo crew, according to the Greek mythology, and the name of this lady, poor lady, I would say, is Atalanta. I will not indeed decide the name, but this is just basically some suggestion. And this is basically the conclusion of my presentation.
Thank you so much to Giorgio there for that lovely presentation. Our next speaker is Charles Hibbitts, who is he's going to talk about NASA's focus group update and the path forward. He is the ISRU facilitator for the NASA Lunar Surface Innovation Team. Charles.
Thank you so much. It's an honor to be here. Thank you for the invitation to talk. I'm going to start by congratulating the Argonaut mission getting to Phase B and ESA for the successful launch of JUICE. So congratulations and all of that. You know, the previous talks really struck me as something interesting, that there's already a lot of synergy and unity in our path forward in terms of developing a sustained and sustainable presence on the surface of the moon in a responsible fashion. It's almost as if we're having a lot of conferences talking about this. So congratulations to ESRIC for organizing all this, and Jerry for your continuing beating the drums, and Clive as well. So what I'll be talking about today is the role of LSII and what LSII is. It is a NASA-funded construct that's run by the Applied Physics Lab out of the Johns Hopkins University. I happen to be the lead of the ISRU focus group, and I'll be presenting specific details on what we've done over the last couple of years and the path forward. So I'm going to drill down a little bit into the nitty-gritty. But I want to start by talking about what LSII is about. So we essentially are funded by NASA, the contract, through STMD, which is the Technology Mission Directorate, which Jerry spoke on the behalf of, to enable the development of technology for the sustained presence on the moon. And these are all technologies, not just ISRU, although that is, of course, near and dear to our hearts, but all the technologies actually synergize together, as you heard today, to form systems. And this is really where APL's strength is in system integration and system architecture, and it's something that each of the speakers spoke to previously, including one of the astronauts touched upon human-machine teaming, which itself is also something we're going to have to deal with and something that APL is addressing. So in any case, you probably read this already. I don't want to delve on on all these words, but our role really is to enable you, and you initially meant you in the United States, but now it's you in Europe as well, to better develop the technologies, identify the technologies that are needed for a sustained presence. So my message to you is really simple. Reach out to me, reach out to LSIC, reach out to the individuals up here in the various focus groups if you see a need, or if you understand potentially how you can interact with development technologies, even in the United States. And one of our roles is to reach across the pond out to you guys, across all the ponds, Asia as well. So I'll put the names up here. It's always important to know who the people are. The emails are basically replace the contact with first name dot last name, and you can reach out to each of us in that case. All right. So our focus group, in situ resource utilization, has very tight relationships with the NASA ISRU System Capability Leadership Team. We have the pleasure to speak with Jerry and Julie Kleinhans almost on a weekly basis. One of our roles actually is to provide unvarnished opinion assessments about we think where NASA's efforts are going and where NASA efforts need to go. So not being government ourselves and actually performing a similar role for the United States Department of Defense in terms of a trusted agent, we actually do assess what NASA is doing, provide feedback, and also recommendations. And each of us, although I glossed over it before, are scientists and engineers, so we're subject matter experts. Right. Don't want to talk about this too much, but it's pretty well funded. We probably have about 20 people working on this part-time. We do have full-time jobs where we're engineers and scientists to keep us involved in the nitty-gritty and day-to-day stuff. So I want to get on and talk about some of these specific things that we've done, which may impact you and may give you some ideas for technologies you want to develop or reach out to us. The first thing that we did was to hold a supply and demand workshop. This, 3 years ago now, believe it or not, back when LSI kicked off, because we wanted to understand, well, how much resources really needed. Sure, we need resources, okay, but how much? What is the supply curve? And well, we were able to get it down to maybe order of magnitude or so variation, anywhere between 10 to tens, maybe 100 metric tons per year, depending on what exactly the architecture is. So we aren't talking about just supplying oxygen for astronauts to breathe. We're talking about the real thing, as you each know already, is providing propellant to refuel the rockets that go. The question is, are we going to be refueling a SpaceX rocket, or are we going to be refueling an Eclipse rocket, right? And that is, in a way, uncertain. But this gives you an order of magnitude to understand what is it that you really need to be designing towards, starting with the demo missions and pilot plans. And it's nice to know that we already are in sync with NASA on that to begin with. All right. Do we need a follow on this? Yes, we probably do need a follow on to this as we learn more and more, and we include things like metal that Jerry alluded to earlier. And as said before, this led to recommendations to NASA. Speaking of which, NASA was initially using follow the water. That transitioned to let's prospect, but also let's focus on O2 extraction from regolith. NASA's focus, I would argue, is mostly carbothermal. A lot of the money has gone into that technology. That's our assessment, so I can say this, even if Jerry can't. It's not MSC, which is nice. A lot of it is actually MRE that's being developed in the United States. So we decided to do a system integration study for MRE design and identify what gaps exist. And we provided this information to NASA. It's not really publicly available, but you know, it's still useful information to us. And we actually are performing a follow-on study where we're going to do a detailed point design for the individual technologies. So not a gap assessment, that will come from it, but do a detailed point design for this is something we could fly, not picking winners and losers, but picking individual technologies so we can assess, well, what is the state of the interfaces? Again, we approach things from a system integration perspective, and if we don't have a very good system integration mindset from the beginning, and this alludes to the terrestrial pilot plant that Mel is speaking of, you know, to later on all, then, you know, we'll merely delay our progress, and we don't want to do that. We need to work together in this. So we'll keep you updated on how that next study goes, where we will most likely identify from some specific gaps as well. As I mentioned, not only is oxygen needed, but actually metal is becoming very important. It's being realized that it may even be more important than oxygen to some extent, depending on whether the rocket provider wants to resupply oxygen or not. Regardless, one will need to use metal on the surface of the moon, either extracted from the material itself or reutilized. So we had kicked off an initial workshop on regolith rebar. How do you take the stuff, how do you get the metal from regolith and put it in a usable form to be used? Well, we don't know, right? What came from this workshop is we have a lot of work to do, not only in the component technology of how to extract the metal, but also how to deliver it. What's the policy for who is in charge of which aspect of it? In fact, the architects cannot contribute a lot to this as much as they wanted to because we cannot tell them what we really were able to provide them to utilize. So I think this is a great area where we can work together as a large community to understand both what is needed and how to get there, again, from an architectural and system perspective. So if you're interested in this and have some ideas, please reach out to us. We'll eventually have a follow-on. Now, this slide intentionally left blank because this is an example of where we actually did some assessments of current NASA technologies. We did this both for water ice you see here, but also for O2 extraction. And instead of showing you the assessments, what we're showing you is that there's a lot of information, there's a lot of technology that NASA is developing that has a fantastic program in both O2 extraction and also water ice, where there's some duplications, but also I just want to say that almost every area is covered, although I'll remind NASA that they did cancel a program or two that should be reinstated. okay? And that is part of our role. So, all right, the point is there's a great plan going forward, and it's being executed, and it's very hopeful, but it does depend on actually finding out where the water ice is. And this is what Clive would be speaking to later, and something that we all are in agreement with, and NASA understands this as well. Although, honestly, it is probably a question of funding. How do we actually get these missions funded, right? One of the first things to do is recognize the need, and as Clive will speak to, I won't steal his thunder. One direction that we are going to go in the Lunar Surface Innovation Consortium is to, again, provide an option. Okay, we're going to say, here's a point design for a series of missions which could be executed, and this is what it would take to execute them. Not to tell NASA this is our recommendation, but it will enable the identification of specific gaps and provide NASA information on the types of resources and also the schedule that's needed. And so we already know that there is water in the South Pole, but the question is, we need to characterize it and how. We noticed within ESRIC that, well, there's some lack of information, and therefore we have the leeway to actually spend some money and do some studies. And by working with you guys, we may identify some new studies that need to be done that we haven't thought of, so please reach out to us if you have some ideas on this. One of we noticed is that, how about a low-altitude mission so we can characterize a reserve or resource, not a reserve yet, resource at the highest possible best spatial resolution scale we can to inform on the next phase of the mission, because most likely going to be iterative mission. We don't know where the water ice is on the moon, period. Let's be blunt about it. We really don't know where it is. And we know some's in Cabeas, but we don't know any more than that. So let's go and figure out how low altitude mission maybe. The point is that by taking all the information that's already been out there, we can have the chance to develop a series of missions that could work. And that's where we're going to go now, and then provide that to NASA as something for them to think about going forward and present out to the community. Other people have spoken to the need for facilities and all. I don't want to delve on this too much, but yes, facilities are absolutely needed. But more importantly, and a lot of them exist, but more importantly, we need to understand what facilities and what these facilities need to be able to do and if they're meeting our needs. And part of that from a system perspective is really what we are calling a lunar proving grounds. One can also call it a terrestrial pilot plant test facility. And Jerry, you had another name for it as well. It's very interesting. We're all thinking about the same thing at the same time. So let's coordinate these efforts. APL, and this is an informal hold the date announcement. The slide's not updated. It actually should be July 12th and 13th, not August, but July 12th and 13th. There will be a hybrid meeting to discuss the needs and requirements for a proving ground, not to talk about facilities themselves, but what would we need to be able to test out there in the field to ensure that the ConOps, the interoperability, the interfaces, the system integration of these systems all work together, so when we take it to the moon, we know it's going to work. So that is really the goal for that. And finally, just want to end on the note that any sustained presence is going to impact the lunar surface. And so, as previous speakers had said, let's do this in not only sustained, but sustainable and responsible, and also inclusive manner. So LSI is certainly, one of our roles is to reach out to the community, but also underrepresented communities, including indigenous communities, and I'd argue take it one step further and reach out to even non-spacefaring nations in this and go forward together. Thank you.
Speaker is going to join us online. So a warm welcome to Dale Boucher, who is joining us hopefully online. I'm sure we'll see him quite soon. And he's going to give us a talk titled Engaging Terrestrial Mining Sector via Spin In and Spin Out. Dale, can you hear us?
Absolutely. Good morning.
The floor is yours.
Thank you. All right, first slide, please. So there is a lot of stuff to unpack here, so I'm going to be moving fairly quickly, and I'd encourage you to reach out later to discuss this some more. I put this slide in because Jerry likes Venn diagrams. So in reality, this is what a mining ecosystem looks like terrestrially. And what we consider mining companies are the the top bubble, the major mining corporations, mid-tier mining companies, and mineral exploration companies. What we don't tend to talk a lot about is the support that these companies get in the form of the original equipment manufacturers and service and supply sides, and industry associations, research groups, pilot plants, incubators, financial regulatory supports. It is a Venn diagram because quite often the major mining corporations will take over some or all of those support functions, although that is happening less and less with things like original equipment manufacture and the service and supply sector. The thing about those two support bubbles is that they don't just service the mining corporations. They will service other sectors. For example, you could think of Caterpillar. And Caterpillar will have equipment that, they're considered an OEM. And they would have equipment that services the mining corporations, but they also service civil construction areas as well. Next slide, please. A mining company, what we call the mining company, is that top bubble, essentially exists on the right-hand side of this little chart. Now, this is a life cycle of a mineral discovery, a little bit different than what Jerry showed earlier, because Jerry showed the value of the company. This is the value of the mineral deposit itself. And you can see that the life cycle extends 10, 15 years between actual concept and final depletion of the ore body. And its value changes quite dramatically. And so the OEMs, all the support groups, live in that entire life cycle, and they will support the activity in some fashion. The mining companies, what we call mining companies, live in that little curved area from roughly the feasibility area through to depletion. And because I'm Canadian, we call that a hockey stick curve. So we have to keep that in mind, that if we're going to engage the mining companies as opposed to the service and support and OEMs, then we have to understand why they live in that hockey stick area. Next slide, please. This is why. This is the ROI curve, return on investment curve, for a typical mining operation in that hockey stick area. Next slide, please. And that red line depicts the investment and return on investment that a mining company will promise their investors as they go into an ore body extraction process. And it shows essentially cash flow. It's something that takes place over 10 to 15 years, and it is typically put in place before they begin the construction period of a mine. So anything that disturbs this return on investment curve from the mining company's perspective is not a really good thing to the investors. And CEOs of large corporations that are involved in the mining sector are very, very cautious about disturbing this line in any fashion, unless there is a net positive increase in the return on investment. Next slide, please. The first way that you can affect this curve in a positive fashion is that you change the timeline for your capital investment. You're still spending the same amount of money. You're just shortening the amount of time that you're gonna run through this budget. And what you're going to end up doing is simply advance the return on investment a little bit. There's no net gain. You're just getting paid back a little quicker, which I guess if you start considering interest rates is a net profit of form. Next slide, please. The second way is to spend less on capital. And now what we've got is we've got some very real return on investments, because you assume that the productivity of the mine, which is the right-hand side of that curve, is going to remain constant according to how what your plan was. But there is an overall net profit over the life of the project. Next slide, please. The third way is to spend the money that you said you were going to spend, trying to get the mine up and running, and change the productivity, become more efficient. Again, you're not really getting much in the way of net benefit other than the fact that you are saving some interest charges, perhaps. Next slide, please. This is perhaps a little bit difficult to see, but it shows the extension of an existing mine, the extension of the life of a mine. And this is primarily achieved by implementing technologies and capabilities that can extend the life of the mine. The way that they do that is that they find that the minimum grade or the minimum value of the ore that they're processing is reduced. That means that they can mine more and more marginally and extend the life of the mine, and thereby gain actually pretty good net profit over the life of the mine itself. Next slide, please. So, if we accept that mining companies are live in that right-hand side of that hockey stick curve, then we understand very quickly why mining companies don't want to engage in risky prototype development or any risky kind of technology development activities. In essence, mining companies live in that high TRL area. Anything lower than TRL 8 or TRL 9 means that they've got to invest in a risky capability, and their investment folks just won't allow that to happen. So it becomes very, very difficult to convince a mining company to take those kinds of risks. There's an adage in the mining industry that says every mining company wants to be first to be second, which simply means unless you can get in there and show that this technology has actually been operating successfully over a period of time in other mines, that they're probably not going to engage in it. So next slide, please. So here's that comparison again of the life cycle of a mineral discovery, remembering that the mining companies live in that development sector to depletion, that hockey stick area. You compare it to the return on investment, and chances are really good that when a mining operation is gearing up and sourcing investors, that's in the feasibility stage. And so that capital expenditure curve is probably not going to vary too much, largely because by the time they start construction on a mine and opening up to exploitation, they have already set aside funds for what kind of equipment they're going to use, what kind of process they're going to use. So that red line on that curve on the right-hand side is pretty much written in stone, and it's not going to change that much. The only way that you can change this curve is by extending the life of the mine, as shown by that dashed line on the dashed green line that extends off to the right, or by changing the efficiency of the production, the productivity in the mining area itself. And so if you can show that a technology or a capability can have one of those two effects within probably a fiscal quarter or two of a mine's life, then you have a good chance of getting the mining company engaged in a fashion that will not get their CEOs fired at their next shareholders meeting. So how do you do that kind of thing? Well, you start looking at things like spin in and spin back. And next slide, please. And so here's a couple of examples of spin in and spin back. Resolve unit on the left-hand side, that was actually a picture taken in Mauna Kea of the Juno rover with a drill on it, and mass spectrometer, sorry, a neutron spectrometer, and a few other little goodies. Jerry can tell you all about it. That evolved into essentially two terrestrial spin backs. One is on the bottom, look, that little orange looking beast. That's actually a firefighting rover that was being deployed in industry, not just in mining industry, but elsewhere. It was evolved from that Juno type of work. The top picture is a small micro drill that was designed as, that was an offshoot from the drill that is mounted on that Resolve platform. That micro drill was then deployed to Bort Longyear in Atlas Copco when it was, before it became Epiroc. And we looked at doing sampling at in an underground application to improve the safety of samples that were required to be taken between blast rounds. And so you can see how the technologies were developed for a space application, the Resolve project. They were migrated into an Earth platform and spun back to Earth. And these small increments are what will encourage the mining industry to begin looking at technologies and capabilities. Next slide, please. There are a number of them. Energy systems, for example. These are just a few examples. There was a diesel fuel cell that was developed part of the shuttle program that used a reformer. And the mining industry has been looking at implementing that as a method of producing hybrid vehicles for underground applications. Mine safety, there was a project that we worked on specifically to look at using some of the spacesuit technology that Kennedy Space Center had worked on as a means of providing rescue breathing air for rescue teams in underground environments. Mining and processing, you can see the picture of that Caterpillar unit over at with a NASA trailer behind it. Caterpillar has been involved with NASA's excavation challenges for a number of years. There's a lot of teleoperation and autonomous operations being developed for space applications, and they are being spun back into the terrestrial mining industry. Next slide, please. And this is my final slide. I'm just going to leave you with this thought that if you want to engage the mining industry, you have to think about the impact of innovation, and you have to think about how you're going to improve their ROI, their return on investments. Whether it's in the service and support sector or OEMs, or whether it's the mining company itself, there are slightly different drivers, economic drivers in each of those areas, but the thing remains the same. The concept remains the same. If you want to engage the industry, you've got to prove that they have an opportunity to make money here. And one of the ways to make money is to spin in and spin back technology development. And I will stop there. Thank you for your time.
Thank you so much, Dale. Well received here in the room, and hopefully you can come and be in person one year in Luxembourg, but we thoroughly enjoyed your talk there. Our next speaker is Professor Clive Neal. Now, Clive Neal is Professor of Planetary Geology at the University of Notre Dame, I think I meant to say, in American version. And the talk is entitled International Lunar Resource Evaluation Campaign, the Update and the Next Steps. And I just want to say, since last year, Clive, you sent me some wonderful links, and I've been having my daily feed of everything to do with the world you live in since last year, and those lovely links that you sent me. So thank you for increasing my knowledge of the industry too.
Well, it's good to be here in 3 dimensions. It is a scary world we live in. So Lisa's been exposed to that through some of the emails that come out, but I'm looking over at my prospecting rover delivery system sitting over there. Two utility rovers on there to actually be part of the coordinated lunar resource evaluation campaign. And this little group that you see up on the slide here, on the title slide, they're an inspiring group, even Jerry. And it is a pleasure to sort of be up here representing them. And the nice thing about this group is if I misrepresent them, they'll let everybody know what I've done. So, Dale was talking about spin off and spin back. And one of the things that I lecture to my students about living and working on the moon is we go up there to make life better down here. And we need to be very conscious. Catherine gave this talk about the work that ESRIC's doing. Fantastic stuff. But there's two things to it. What is the spin back potential to this planet? What is going to capture the imagination of our policy makers and our decision makers and our funding agencies that are going to make them want to fund this type of research? It's that spin back potential to make life better down here. And it's really important to remember that if we want, and I'm going to use the S word here, a sustained and sustainable presence on the moon, and dare I say, a permanent presence on the moon, which is what it states in the current US space policy, that we will create a permanent human presence on the moon. Well, that's going to cost a lot of money. And to make that sustainable, we have to do it by making life better down here. So keep that in mind as we go through these the talks and the discussions this week, that spin back is really, really important for making this a sustainable effort. And it's already showing promise because of the new commercial interests. I did some statistics about the company growth in the United States. And pre-pandemic, it was over 100% job growth. And even during the pandemic, when a lot of people were being laid off, it was over 60% job growth. So this is a growth industry, and I know that the undergraduates at my university are really, really enthused about it, and they want to get involved. And part of that spin back and sustainability is the creation of jobs. But what about the resources? We heard the term resources. Bernard gave a great talk about what ESA is doing. Catherine talked about what ESRIC is doing. But until we know the reserve potential of these resources, these are great experiments. Where do we send the pilot plants? Well, if we're going to do oxygen from regolith, we can go anywhere. There's about the same amount of oxygen in the regolith no matter where you go on the moon. Maybe that's our one and only reserve that we have now. But there's two roadblocks, and these are the reserves. Have they been noted? But also, in order to have a reserve, it assumes an economic sort of potential, but there's no demand. So who is going to create that demand? It's going to be space agencies. It's going to be governments. We are willing to buy this much because we want to do this, and we're going to be there for the long term. In NASA's latest document about the Moon to Mars objective strategies and development document, Bill Nelson states we go back to the moon to stay. That's pretty definitive. Now, is NASA going to stay? Probably not. But we need to bring in the commercial enterprise to take over from agencies, but the way to do that is to get rid of these roadblocks in this ISRU value chain. We need to know the reserve potential in order to create business plans, but we need the markets for those commodities in order to close the loop. So ground truth data and demand and markets need to be established to understand if resources are actually reserves. Otherwise, what we're doing is great scientifically, creating a lot of new knowledge, but we really need these ground truth data in order to move forward and go to the next step, send these pilot plants to the correct locations on the surface of the moon. So what have we been doing? Well, just a quick brief history of this little group. Started at the LSIC 4 meeting. We then gave a talk representing the group virtually in 2D last year. at this meeting. James Carpenter gave a talk at the IAC in September last year, and then we had 2 virtual workshops. And I'm just going to briefly give you the results of those 2 workshops. It basically highlighted the data that we need to get in any resource prospecting or evaluation campaign. And you can see the types of data there that we need. It's fundamental data at the granularity that is much, much finer than we get from orbital data. You know, the idea that Karl talked about with the neutron spectrometer, those are kilometers pixel sizes. We need to do better if we want to send surface assets there via the Argonaut lander, just putting it out there as a way to move this forward. But many of these data types are going to be needed from mobile surface assets. If we look at the top 10 most promising PSRs, permanently shadowed regions for polar volatiles, you can see there that the top 10 cover over 6,000 square kilometers. That's a lot of real estate. This is why this has to be an international campaign. It has to be a cooperative campaign. We have to go there together with the eye on making life better down here by going up there. So looking at the more from number 17, the Lunar Surface Science Workshop, again, coordinating data gathering efforts. We start with the current funded missions and those that are already at the moon to provide information on the different resources. We need to define the explicit measurements and fidelity needed to derive useful data, developing lunar resource and reserve standards and evaluation metrics. I did drag my carcass out of bed at 3:30 a.m. last year to watch Carlos Cespagel give a wonderful talk about the lunar ore reserves standards. And we need inclusion of partners in this effort, including non-spacefaring nations. And Karl talked about that with the Lunar Surface Innovation Consortium. What are the data policies? How are they going to work? What about exploration rights? So there's legal aspects that need to be thought through. Leveraging private industry, and Dale showed us how we can leverage that, and then developing a list of high-priority targets using existing data sets to focus surface exploration, and then mission concepts that could be a quick win for any resource evaluation campaign, getting better resolution neutron spectrometer data over the lunar poles. And then number 18, we need to define lunar reserves. So maybe do a reserve potential map on the basic current data sets to highlight those data that we need to be able to move forward. Data products will be highly processed, so standards are going to be critical. Resource discoveries can only be claimed once we have ground truth surface data. And then a coordinated international lunar resource evaluation campaign is compliant with the Outer Space Treaty. This is why I do like the Artemis Accords. They bring together spacefaring and non-spacefaring nations in a common goal to go to the moon and beyond, but also to take everybody with us on the way there. And again, it enables cooperation at various levels of involvement. It creates diplomacy and communication in a time that so desperately needs that type of thing to go on. Space is the place that can bring people together. It increases efficiency and reduces costs to any one nation. And it said should be coordinated by a neutral broker. Now, what does that mean? Well, I have an answer for you, but I'm not going to give it right now. So, next steps. Identify the founding partners and convene an international preparatory meeting for the campaign. Identify a neutral entity to be the coordinator. Develop reserve standards, information requirements, and produce much needed data. And again, laws. We've heard a lot about laws. And again, this is, I think, maybe the foundation upon which we can build a lot of what we discussed in LSSW 18. So beginning the coordination, you have there a list of current and scheduled missions to go to the moon. It's not exhaustive, but you can see there, it's not just the USA. Everybody There's a lot of international participation, including from nations that may not be willing to sign the Artemis Accords. So who does the coordination? How are we going to coordinate these types of missions to get different data sets on the same location at better fidelity than we already have? So we know exactly where the Argonaut lander can go and deliver those prospecting rovers. So expanding the coordination, refine through peer review the law's concept. Inclusion of partners, Artemis Accords or other ways of doing it, agency-to-agency agreements, target identification based upon existing data, leveraging commercial industry, and again, Dale spoke to that, and then a potential reserve report for the moon based upon our data that we have to highlight knowledge gaps. And again, there was this space economy workshop that was held just earlier this month, technologies to fill observation and capability gaps for the off-world mineral resource economy, and that was a NASA, United States Geological Survey meeting. It was very interesting. So, the way forward. Here's that list of missions again that I think we can coordinate. And by the we, I mean the community. I spoke to a couple of principal investigators of these missions. You can actually request targeting on their mission websites. We can request those targets to get different data sets on the same location. We can do that now. Why don't we do that? I think that is going to be the way forward to show that we, as a community, can begin that coordination. We're going to have an international virtual workshop, and again, maybe through Lunar Surface Innovation Consortium, maybe through ESRIC. Work with mission PIs to ensure that multiple data sets come from the same target and integrate with current data sets so we can get these reserve report for the moon up and running that is actually quantitative and useful. And then we can then define surface targets for these assets to go and get this ground truth data and actually start moving the whole ISRU forward into the critical path for human exploration. Thank you very much.
Thank you so much, Clive, and lovely to have you here in 3D, as you said. Also want to point out that Clive has a fabulous tie on, and he's not the only one with a space tie. So along with looking at the posters and the wonderful moon exhibits out there, you can have a nice kind of session looking for various ties and accoutrements linked to space, because there's quite a variety on offer here today. Our next speaker, Dennis Harries, who's going to give us an overview from ESRIC.
Thank you, Lisa. So, good morning. I'm not sure if it's still time to say good morning. Moyen, as we say in Luxembourg. And I have the pleasure to introduce the current research and the planned research that we are doing at ESRIC. But this is essentially not possible without introducing the team. As Catherine mentioned this morning, the team is very diverse. We have a very diverse set of backgrounds, and also please come and meet us. Find us. I'm giving you hints in my talk, whom to ask, what about, and the diverse background is very important for us in space resources. So on the right side, you see this very complicated diagram. Catherine loves it. And the ISRIC ISRU Technology Gap Assessment Report has an even more complicated version of this diagram with many more of these vectors and links between the various compartments of this space resources economy. So we're talking very often about end-to-end processes, which sounds like kind of a chain, but actually this chain is a very complex network of links between various compartments. And essentially, it should be also a circular network to make this economy sustainable and responsible. So our approach is to put our projects at various places in this network. So on the left side, you see the numbers corresponding to these compartments of our projects. So I cannot show all of them. We work with various partners. The most important partner, of course, is ESA, which I will show some examples. And we're also working with the industry, with Air Liquide, with Airbus, and Manna Electric, for example. And a shameless plug for a couple of posters. So Ivan, Vishnu, and Timon will present some of their work in a poster session. And what I will show, just as a brief spotlight, are 3 projects we are currently working on, which are centered in the middle of this network. So the first thing, if we again change back to a kind of chain end-to-end process, is beneficiation. So this slide shows you beneficiation, or what would happen if you did not have beneficiation in a ISRU process chain. You start with your regolith, you do some kind of chemical processing, you have an intermediate product, you purify it to have your final product. So in this purification step, you create a lot of waste. And because you started just with a raw regolith, you dump a lot of energy, a lot of joules per kilogram in your waste. So of course, this is not something you don't want to do because it is clearly not sustainable. We want to avoid waste and we want to avoid dumping energy into waste. So beneficiation splits the material stream very early on in this process chain to separate, on one hand, the material into different streams, to process them separately, to decrease the waste volume and the energy you dump in this waste, and to increase the yield of these downstream processes, and also reduce the contaminant inventories in these intermediate products so that the purification step becomes more efficient. So what we are currently doing, and this is the big challenge in ISRU beneficiation, we're trying to find processes that do not rely on the use of water or on the use of gases, which are very limited in the lunar environment. So we are looking, for example, at ballistic processes in low gravity environment, where we, for example, could use electrostatic processes to separate minerals by size and by type to facilitate this beneficiation process. Another project I'm very much involved is the Alchemist demonstrator, which is a loan from ESA. So this is a hydrogen reduction system, which always confuses me because we don't reduce the hydrogen, we use the hydrogen to reduce iron inside ilmenite, so the iron titanium oxide that is fairly abundant on the lunar surface. So we produce metallic iron, titanium oxides, and water. So we extract the oxygen in the form of water. The process is relatively simple, but it has the drawback, it has a very low yield because the abundance of ilmenite, although it's one of basically the most important or abundant iron oxide on the lunar surface, is still in the percent range. So it's not very efficient to use just the raw regolith. So here, beneficiation comes into play to enrich the ilmenite in the material, to have also less contaminants in this process. Another aspect we are looking at, especially in cooperation with LIST, with the MIT department, is to use plasma. So if you dissociate the H2 molecule, you get a much more reactive gas. So either you could have atomic hydrogen or ionized hydrogen, and this, in theory, is able to reduce much more of the metal content, also the titanium, release much more oxygen in the form of water. So this is also a focus. Currently, we are in the commissioning phase of the Alchemist. We are setting up the system, and what we will do once it's running is to look at the process thermodynamics, look at the kinetics, see how this relates to the yield, how can we find optimal stopping points of the reduction process, and also we want to quantitatively assess the impurities that are generated in this reduction process. And this gets me to the third project that we are working on with Air Liquide. This is the next step to purify the water, and we're also working on the purification of oxygen, but here I focus on the water. And for this, we are looking into a process called the vacuum temperature swing adsorption. The figure on the right side is a very much simplified schematic of this process. So the challenge here is that the water that comes out of the alchemist, or the water that you find in the permanently shadowed regions in the lunar poles, contains multiple contaminants at very variable concentrations, just to name H2S, ammonia, CO2. And some of these contaminants, especially something like ammonia, has a very high solubility and a very high ability to dissolve in water. So traditional separation technologies like distillation have big problems here. And on the other hand, these contaminants are actually interesting and very limited resources on the lunar surface. Nitrogen and carbon are contained in them, which are really rare on the lunar surface. And so what a purification system should do, it should selectively remove these contaminants so that they can be processed for downstream applications in this chain. So we're looking at this adsorption process. So basically it consists of columns with a highly hydrophilic alumosilicate adsorbents, so zeolites, and these are cycled alternating between adsorption, where these zeolites are loaded with the molecules, and desorption or regeneration, where these molecules then are again removed. And by fine-tuning this process, the pressure, temperature, and time path, it is possible to tailor this to a very specific contaminant inventory. And this somewhat summarizes, again, this is just a chain, but this is our start. And we think that this linking is a very important aspect of the work that we do at ESRIC. So what we will have in the future to come is a molten salt electrolysis demonstration lab, also being provided by ESA. So where we will study the generation of oxygen directly from the regolith, also the production of metals, mostly focusing on aluminum and silicon. So you can visit Timon's poster, who's already working on this at ESA, at ESTEC in the Netherlands. We expect this to be operational by the end, or to be delivered by the end of 23, and to be operational at some point in 2024. And the other big thing to come in the future is the dusty thermal vacuum chamber at ESRIC, also provided by ESA, which then will allow us to take these lab-scale demonstration processes to the actual relevant environment to progress on the TRL scale and test these single steps, and then in the future the connection between these steps in a vacuum condition that most closely tries to mimic the conditions on the surface of the moon. So, and of course, these links are almost always in a cooperation with partners. And initially I mentioned this complicated network, and with many, many more links, if you look at the ISECG report, you will find many more links. So we will need many more partners for this. So you're welcome to approach us and find out how your role could be here in ESRIC to support this research. And with this, thank you.
Thank you so much, Dennis. And there's plenty of people from ESRIC here that you can chat to through the course of the conference. Now, our next speaker, he's habitual member here of the conference, Space Resources Week, and it's wonderful to have him here present in person again. It is, of course, Ángel Abbud Madrid, who is the director of the Center for Space Resources at the Colorado School of Mines. Ángel.
Resources and of the space resources community never ceases to amaze me. It's unbelievable. Hello, everybody. It's great to be back in Luxembourg to be able to give you an update of the activities that we're doing at the Center for Space Resources at the Colorado School of Mines, where we cover basically what has been talked about, what's called the space resources value chain. So we conduct work on fundamental research. We do work on the prospecting and exploration, the space mining, which includes the excavation, the drilling, the extraction, work on space manufacturing and construction. We do work on space infrastructure. We get involved in the very important dialogues about economic, legal, and social aspects. And of course, because we are a university, we get involved in the transfer of knowledge to the students that are very interested on this field of space resources. So what I'm going to try to do here is to give you an example of each of these activities on projects that we're conducting at this very moment. So let's start by just fundamental research. What are those resources that are viable to extract on planetary destinations? One of the most recent work by Professor Kevin Cannon is to revisit what are the possible ice the stratigraphies, how that the ice was formed by different types of water deposition, and how this has been changed by the churning of the material in the upper surface of the moon. This is important information because, as has been talked about, we want to know as much as possible where the ice is. So we're using as much data as we can at this point to find this out. Same philosophy applies to trying to find, in a joint work that we're doing with a company called Astroforge that's interested in asteroid mining, on trying to pinpoint what are the potential elements that could be of interest in asteroids as compared to terrestrial ores. This is key information for companies or organizations that are interested in extracting resources from asteroids. Also, in fundamental research, we continue our work to produce higher fidelity simulants and to characterize them, and also to keep updated what is probably the most extensive database on simulants produced all over the world for Moon, Martian, and asteroidal simulants, a work that it's on its own quite a task. We're also in the pursuit of high-fidelity simulants. We are part of the project Doomflow. This is a SBIR from NASA. We also work with Blue Origin and the company Icon. And the whole purpose of this is to try to compare what are some of the properties, in specifically flowability, like the angle of internal friction, from a simulant to a real Apollo simulant that was brought, Apollo samples that were brought to Earth 50 years ago. And so what we try to do here is use, and hopefully by the end of the year, we will be able to go on board the New Shepard on Blue Origin. It will take us to suborbital flight, and for about 3 minutes, we will experience not just low gravity, but this capsule can rotate and give you 1/6 gravity. And so during that time, we can do experiments with various simulants and with the real Apollo samples. I'm going to show you a video of what we have done here on Earth. This is simulant, but there will be different cells with different simulants and also the Apollo samples. And so what we're going to try to see is how this extremely cohesive material that is on the lunar surface can flow at different angles. And this will help us to see how simulants compared to Apollo samples, and that will help us to make better simulants and also to figure out how we're going to do excavation and movement of this material once we get to the moon. So hopefully we can do this by the end of the year. In another work that we've been conducting for several years now on geotechnical properties, we continue to try to simulate as much as possible the environment that you're going to have on the moon. So we use a dirty vacuum chamber. We also use cryogenic temperatures. And what we try to do is use lunar regolith combined with ice. So this is icy simulant, and be able to obtain properties like penetration and relaxation of this different material so that we can gather this information that can help us by the time we get to the lunar surface. So that's the whole point of doing these terrestrial experiments. Now, that moment of doing the experiments on the lunar surface hopefully will come in 2025 in what will be our first project on the surface of the moon, in which we have aligned with Maxar Technologies on this project called Sampler. That will take us to the surface of the moon, and we will be able to do the same type of experiments that I just showed you on terrestrial laboratories, use the same type of penetrometer. And also, we will have a scoop so that it can tell us how easy it is to get a hold of this material. It will have some seeds so that we can have sort of an idea of the average particle size that you have there. And we will have plenty of cameras to see this type of behavior on the surface of the moon. In the area of prospecting and exploration, we just graduated our first experimentalists on the Space Resources program, Curtis Purrington, that conducted some tests with a very novel technique of how is that you can get an idea of the water content on the lunar surface if you go there, instead of having cores and drilling techniques. And so what this consists of is being able to have a thermal probe that would inject energy. Then we will see how the thermal wave propagates along that medium, and given different water content, we can see how the wave changes with time. So this is a great, very compact technique that anybody can have on a drill or whatever tool that you have on the surface of the moon, and be able to see immediately or get an idea of the water content on this medium. In the area of space mining, we just won an award for the Big Idea Challenge, in which a series of students got together to conduct an experiment that will consist on the extraction of metals. This is something that has been mentioned that is very important. It will use a molten regolith electrolysis technique, but more importantly, that the oxygen, which has been the objective most of the time, is about the metals. How is that we can get a hold of them? So the lab system consists of mainly the core operations in the middle. So you have the reactor, you have the refinement, and finally obtain the molten metal. And this is how the experiment will look if you were to be on the surface of the moon. It has different stacks consisting of first of all, the MR, the molten regolith extraction reactor. Then you will have the metal refinement, and eventually have the metal. And the whole point here is to be able to extract different metals at different stages. So first you get your silicon, your magnesium, your titanium, and eventually your aluminum by changing the voltage on your unit. And so the main purpose is to get the metals. Obviously, as part of this, we will get the oxygen at some point. But again, the importance is to start extracting the metals for a variety of applications. In terms of space mining, again, what do you do once you hit the water? The water, you have to electrolysis to get your hydrogen and oxygen for your propellant. So we just finished a work, and that we hopefully will continue on how to do this with solid oxide electrolysis. This is different from the alkaline water electrolysis, and it's promising in terms of the low energy that is going to be used for obtaining the hydrogen. So we conducted experiments inside a vacuum chamber that was also thermally equipped, so to give us the temperatures on the surface of the moon. And interesting enough, it gave us really low values of how much energy per kilogram of hydrogen you can get. So this is a very important work. And the other thing is that you're going from steam to hydrogen. You don't have to go from liquid to steam and then eventually to hydrogen. So that reduces the effects of low buoyancy transfer that you get on 1/6 gravity. One of the newest projects through what's called the Luster NASA announcement is the Project Aspect. If you're going to go to the moon and you're going to have a landing pad, you need to prepare the surface. If not, you're going to encounter all sorts of rocks and craters. So this is what this project is all about. And it is in combination with Michigan Tech and working with Lunar Outpost and also with a large construction company like Bechtel. And so the whole point here, what we're going to be doing is outfitting what is already a rover from Lunar Outpost, and we are going to add just one tool, and that is a blade. The blade will pick up the rocks, will pick up the regolith, it will be able to grade, it will be also able to compact about 10-meter diameter pad up to 30 centimeters, giving you about a 90% of relative density. So this is an exciting project that is going to get underway this summer. And finally, we are a university. So we continue being interested on educating scientists, economists, entrepreneurs, and policymakers on this field of space resources. This is our 6th year that we introduced this new program that is providing via online certificates, masters, and PhDs. And to this point, where we are right now, we are up to 132 students from 5 continents, from 22 countries, with a very diverse type of backgrounds. We got from engineers all the way to lawyers, lawyers all the way to engineers, if you want to put it that way, and all sorts of fields. And what this represents is the excitement in the level of interest of people all over the world in the field of space resources. And this is a very important thing to nurture, because these are the people that are going to make this field possible. Now, it's great to come to Luxembourg because it gives me the opportunity to get to know the students in person that I just see in screens when I'm teaching these courses. Actually, this morning I just met 6 of them, and it's a great opportunity. But the hope is that in just a few more years, not only we get to teach students from all over the world, but imagine what we can do if we can train and educate those people that are on their way to the moon and being able to actually tell them what they're going to see there. And by the time they get to the moon, for example, Maurice Morer can actually tell the students, this is what regolith looks like. And this is the way that you should do your experiments here on Earth. And so that's the hope, so that we can make these not just fully online, but fully interplanetary. Wouldn't that be exciting? Thank you.
Thank you so much, Angel. I absolutely love the energy that the professors who speak here bring to us, and it's an incentive, an invitation, as has just been given, to go and do those PhDs that people never got around to doing earlier in life, perhaps. Our next speaker, another wonderful speaker, this time from Japan, professor of the Department of Solar System Sciences, ISIS JAXA. Please welcome to the stage Professor Tomohiro Usui.
Thank you very much for inviting me to the workshop. And okay, here's my slide. JAXA successfully completed, in the last 2 decades, successfully completed the 2 asteroid sample return missions. And then again, significant knowledge about the asteroids. Now I'm giving a talk about how JAXA sample return program appreciates the scientific and economic value of asteroid resources. So I'm very, very delighted to be here to give a talk, to present like a JAXA sample return mission and then move it on. Yep. That chart shows like JAXA's small body exploration strategy program. Back in 2010, we successfully completed the Hayabusa mission that returned the sample from the S-type asteroid. S stands for Stony asteroid. Then 2 years ago, 2020, the Hayabusa 2 returned the sample from the C-type asteroid. C stands for the carbonaceous-rich asteroid. And both these asteroids are near-Earth asteroids. In 2029, we will go to the Mars orbit. So JAXA's strategic small body exploration program will go beyond the snow line and outer solar system to have more primitive, more voltage areas. And also the MMX stands for the Martian Moon Exploration Missions, is a kind of plays a pivotal role from like small body mission, also the large body mission, because the MMX is like a Martian moon system. So the JAXA MMX, through the MMX, the JAXA will step into the Mars program. Okay, here's what we have learned from the Hayabusa 2 successful asteroid sample return missions. And we went to a C-type carbonaceous asteroid, Ryugu, that you can see on the left, right, actually, from your side. And it's going to be 500 meters in diameter asteroids, lots and lots of volatiles and carbon in it. And what we found is to have the first accurate estimates of water content in the carbonaceous-rich asteroid. The result is that the sample contained about the 7% of water in it. But I just want to know that, or caution that this is not the free bond water, not the H2O, but occur as structurally bonded water in the minerals or interlayer water of the minerals. So if you want to use that water as a resources, you need to not just crush it, but to crush it and heat it up to release the H2O gas. And also, as I said, the Ryugu is a carbonaceous asteroid, so that we have a bunch of the carbon in it, about the 5% of the carbon in the samples. Most of the carbon occur as organic matters. What kind of organic matters? Here it is. The sample analysis we conduct, because of the sample return mission, we conducted like details, the analysis in the lab, in the Earth. Then we find out that 20,000 types of organic molecules found in a Ryugu sample, and most of them contain amino acid, alpha-lic amines, PHAs, lots of types of the organics in the samples. And what we found more interesting is that some of the organic molecules contain the essential products of the living organisms. You can see on the left, the uracil, which is the nucleic acid that's a kind of ingredient of the DNA array forms, and also the niacin. You need a vitamin for the living, the metabolisms for the living organisms. It's a very trace. These are the very trace components in a Ryugu sample, but you have. And also pointed out is that I should wanted to mention is that these are not of the results of the terrestrial contaminations. I am a manager of the JAXA's creation group. I'm for sure that like these are not from the hairs or something related to us, but really from the space. Okay, what's next for us? As I said, we will go further and further, or more primitive, or more cold, or water-rich regions. How about the D-type asteroid that could have originated in our solar system? We plan to go to the Martian moon. Martian moon Phobos or Deimos may represent that kind of D-type asteroid that originated in outer solar system. JAXA will return the sample on Phobos in 2029. We will launch the spacecraft in 2024, and then we're going to stay at circum-Mars orbit in 3 years, and from 2025 to 2028, and do some remote sensing and sample retrievable activities for Phobos, and get the sample back about 10 grams or more, and return to the Earth in 2029. That's it.
Thank you so much, Tomo, and I enjoyed looking at those chemical structures because at least that's my background and I did understand it, so really, really interesting. Actually, I'm super impressed by the amazing research that we have globally, so it's really inspiring, and year on year it gets better. Our next speaker is going to give the overview from Imperial College London, and he possibly has the best name to do with space. It is Stanley Starr.
No one ever told me that before. Thank you very much to the conference for inviting Imperial College London back for another annual update on our work. And I'd like to thank Jan Silliers and Catherine Hadler for supervising this work. Catherine was at Imperial, and now she's transitioned over to ESRIC and is still involved in the PhD students' work, which this is mostly composed of. Now I have to. Okay. The main focus of our work is beneficiation, and you've already seen a number of presentations that mention beneficiation. It's a key aspect of terrestrial mining. It's very common for terrestrial mines to have low concentrations of the ores that they require and to go through some sort of process to increase the concentration as high as possible often before they go into their processes. And these are some charts from previous papers that have been published by Imperial showing the effect of ilmenite concentration changes on a number of aspects of a lunar mine. I should also thank Josh Rashira, who did these charts, but he also did all of the charts. And he's made comments on the charts, by the way. If you download these, you can see his comments. But it also substantially increases the confidence. You wouldn't want to go to the moon with a mining setup and then not reach your production goals, require too much energy to get there. So beneficiation is an area that hasn't received sufficient attention probably. And like everyone else, we don't know how to do it either, but we have some good ideas that we're following. This chart shows one of the graphs that Kosuke Aikiya produced just recently in a systems engineering study, and it's on poster number 17 out in the hall. And he's looking at analyzing and optimizing dry mining for oxygen, ice mining for oxygen, and a hybrid, looking at the trades in between those three different options. And it's early work, but he's already come up with some very interesting observations about the Bayesian and Monte Carlo analysis that he's doing. And he's also doing component level modeling. And I don't know if this is going to work. Oh, here we go. Luca Malone developed a video game format optimization tool. I apologize, it's going so fast. It really doesn't go this fast when you play the video game. This is a little bit more like it. But what happens is a user, so he's tying into not artificial intelligence, but human intelligence. So a gamer plays the game and selects their architecture for rovers, processing plants, oxygen storage, the various elements of a lunar mine, and then lets it run, watches how the commodities and the energy use goes, and then they can modify it and run it again. And so he's having students at Imperial play the game and gathering and harvesting the data from them and looking at the overall landscape of optimization. And it is a lot of fun, unless, of course, everything goes badly. then it's not fun. This is kinetic sieving, is a fancy word for shake it and see if it separates. But the animation, we did not produce the animation on the left. That's taken from somewhere else on the reference. But this follows on some work that Victoria Shine reported on last year, and she's now with ESA, where samples, 1 gram samples of 4 different lunar simulants and an Apollo sample were vibrated at different frequencies and amplitudes, and we looked at how they separated, with larger particles coming to the surface. And the reason this is up here this year is that we're doing much more detailed analysis of the micro-CT images and data that we received to try to figure out what it is telling us, because we're going to do next steps, but we haven't exactly figured out what those next steps are. We're trying to extract everything we can out of the data that has already been taken. This is UAU's work, and I don't want to take too much thunder. He's going to give a paper here tomorrow. But he's been working on electrostatic traveling waves as a method of transport and separation of particles. Of course, the regolith is all of these tiny particles, and for beneficiation, you'd like to get rid of the really small particles, and of course the really big particles, but they're easier to get rid of, and also sort them more specifically by size and by mineral content. So UA's done this exhaustive mathematical study of how these systems work, interdigitated electrodes that you apply varying sinusoidal voltages to, and this exerts forces on the particles causing them to move. So he's identified various modes of motion, and in the last year he built an apparatus. He's been taking lots of videos and tracking the particles. His theory works extremely well, and in the last couple of weeks he was able to take ballatini of 2 different sizes, and the big ones went one way and the small ones went the other off the ends of his array. So he's really made some significant advances, and he'll be talking about that tomorrow. This is work that's done by Ruben Cruz, and he has been doing foundational work on the tribological charging of particles. And just when you thought everything had ever been said about tribocharging, you really need to read Ruben's work. It's fascinating. This is his last set of experiments where he charged a particle in a vacuum chamber. So, and this is, I believe it's polyethylene. And so he has this automated device that charges the particle in a charger, flips it over, and then measures the charge, flips it back over, charges it again, and so on and so forth. And so he's measuring the saturation charge. When does the charge no longer change? With vacuum level, with pressure. And so he sees normal saturation at atmospheric pressure, and as the vacuum chamber pumps down, he gets less and less charge because the dielectric strength of air is less. And so basically, if there's even a slight amount of atmosphere, these particles can't hold their charge. And then once you get down to where there's very little air, the charge rate increases. And it's not shown here, but basically it increases till the particle won't leave the charger. It's stuck to the charger with the image charge. Josh Rischera, this is one of his recent pieces of work where he was doing a DEM modeling of a tribocharger. So he wants to have good contact as the particles flow down from a funnel, and then he's flowing this into an electrostatic separator. So he's got 2 plates, he's got a whole series of grooved receivers at the bottom, and the particles go in, and based on their charge, they will separate out into these different trays, and he's shown excellent separation with the device. But this was to prove the concept of using DEM to optimize a charging device, which he did, and that's his data on the right. And I believe, if I'm not mistaken, that's it.
Thank you so much.
Thank
you very much for showing us the work of the group and everything there that's happening at Imperial, and we look forward to those papers over the next couple of days. Next speaker, Professor Philipp Reiss, who is the Professor of Lunar and Planetary Exploration Technologies at the Technical University of Munich.
Right, thank you for the intro. Yeah, exactly. So TU Munich has been active in ISRU-related research for many years now. Since more than a decade, we're inspiring and motivating, educating students in space resource utilization with various courses that we offer, various involvements and projects, also flight instrumentation, as you will see on the next slides. So given the recent expanding of our Department of Aerospace and Geodesy, I will now give a brief overview about what we're currently involved in, and to give you sort of a showcase of three main research pillars. So this is just to give you some context information. As I said, we have recently expanded a lot in the aerospace domain, in the space domain specifically. We now have a number of professorships, as you see here, and are still expanding. So my group is working on lunar and planetary exploration, mainly surface-bound robotic exploration of planetary bodies. Then we have a new position on human spaceflight technology. We have people working on space propulsion and mobility, specifically also one group dedicated to pico and nanosatellites. And there's a few positions on remote sensing and geodesy. So with that, we sort of address various elements along the ISRU value chain that you see depicted on the right-hand side. So covering prospecting, characterizing resources, which we heard about a lot already today, then also the extraction part and the processing to produce products, but we also have the stakeholders in the utilization part with people developing life support systems, people developing propulsion systems. So in that ecosystem that we're currently building in Munich, in and around Munich, we address many of these elements, and we have various cross-discipline projects now running, also looking into how to connect the dots in the various research fields. So here are three research foci that I want to present today that are related to space resource utilization. The first one is regolith volatiles interaction. So here we're interested in learning more about the lunar water cycle. We want to understand how water arrives at the moon, distributes across the moon, migrates through the subsurface, what levels of hydrogen species we have in the exosphere, how they interact with the surface, and how they then go on to create subsurface deposits. So here we really want to understand how deposits build up, if resources can build up to be reserves, and support the prospecting efforts that are currently ongoing. We also demonstrate the extraction of gases from a sample in support of, for instance, the prospect instrument development by ESA, where we try to better understand when which gases release and how they interact in order to better characterize samples in situ. We also have lunar thermal environment simulations that you see on the second picture here. So we can simulate lunar surface temperatures with vehicles, objects on the surface that are also moving along, so we can simulate astronauts traversing, rovers traversing across the surface, and how they interact with the environment, and that is specifically interesting for PSR exploration. The second research focus is on instrumentation and sensors. So we're supporting ESA's prospect instrument package development. So here we're involved in the development of the sample ovens that will be instrumental in characterizing the resource and also provide potentially one of the first in situ demonstrations of ISRU processes. We are also contributing the electric permittivity sensors that are, so one of them is integrated in the drill, and this is the second critical element in order to determine the abundance or the existence of subsurface ice. Coming from there, we're moving on currently, developing different Well, derivatives of permittivity sensors, they can sense the regolith, they can detect density changes, but they can also detect ice. And among these is, for instance, the middle picture here that depicts a patch electrode that you can easily mount on a rover wheel. And while roving along on a traverse, you could easily sense the shallow subsurface for water ice. Then one of the developments or instruments that we have been developed for over a decade now is the Lunar Volatile Scout. It's a small compact instrument that can be used to analyze volatiles in the shallow subsurface, so a couple of centimeters deep. The concept we're following here is we don't want to bring the sample to the instrumentation because we want to preserve the sample. This is why we bring the instrumentation to the sample. So this is a drill that encapsulates the sample and then has a small miniaturized mass spectrometer sitting on top, which is provided by the Open University in the UK. And with that, we can easily detect water, but also other volatile species in the shallow subsurface. And the last research focus I want to talk about is the actual processing of water, oxygen, and metals from regolith. So here we are aiming to address technology gaps, such as regolith handling and transport. We have investigated dosing systems in partial gravity already a few years ago. We have more recently looked into conveyance of regolith to connect different elements of an ISRI demonstrator, for instance. So this specifically looked at vibration conveyance. We investigate thermochemical reduction processes. This was also in support of the Prospect ISRU demo. And the picture with the bubbling regolith shows you one of our fluidization attempts, and we have systematically studied how well different simulants can be fluidized in a reactor in order to enhance reactivity and thermal, heat and mass transfer in the reactor. And I will point you here to two posters of one of our PhD students, Francisco. He is working on a holistic modeling of ISRU systems. So this is the flow chart, or the chart on the top of the right, where you see different elements of an ISRU system. We model this based on models that we have developed over the past years in support of life support systems, understanding life support systems on the ISS, but also portable ones. So this framework is now being used to assess ISRU systems to enable top-level decisions on how to combine and group various elements to produce energy flows, product flows, and so on, to understand the full picture, which we think is quite important to assess. Right, and with that, that's it from my side. I'm happy to discuss and meet new people around in the next days.
Thank you so much, Philipp. And of course, an encouragement to keep sending your questions online, because they will be answered by the professionals here or by other people within the community. Our next speaker, David Karl, who has the Twitter handle @SpaceCeramics, that says it all, I think, from TU Berlin, joining us online. Can you hear me, David?
I can hear you not so well. Can you hear me?
Very clearly. The floor is
Wonderful.
yours. Hopefully we'll see you also quite soon.
Thank you. So I could have talked here about the research activities of my research group at TU Berlin and the other research groups at TU Berlin and Space Resources. But I think this week we're going to witness something very major, and I wanted to dive more in detail into that. So I'm going to talk about material selection for in-space manufacturing based on embodied energy and proposals for a space clay economy. I don't have the clicker, and I hope it'll not be a complete slide chaos. So next slide. Next click. So I think this week we're going to be in the second space age. So welcome everybody. When we see Starship launching, this will be the first time that we have very much increased capabilities to actually the Apollo age. So next slide. And what if let's build a space-based solar power station in GEO. So how would we actually go about that? And I want to talk a little bit about the materials we could choose for that, because we have heard today a lot about beneficiation. And I think a lot of the engineers in the audience consider exactly the same materials that we use on Earth for use in space. And I think this is a misconception, and to my opinion, we should consider other materials. So if you go to the next slide, and the next slide. So Mike Ashby has done wonderful work on material selection. And if we look at the embodied energy of materials, including shipping, if you look at the ceramic section here in yellow, you see ceramics have the lowest embodied energy. For example, brick and concrete have the lowest embodied energy. So sintered brick has an embodied energy of 3 megajoule per kilogram, calcium concrete of 0.7. And if you go to the next slide, we have adobe clay brick, which has 0.0 megajoule per kilogram, which is 100 times less actually than sintered brick. Next slide. Next, if we now look at the following scenario. So we use a Starship to go from Earth to GEO using no in situ resource utilization. Then one Starship could deliver 18 tons of materials, increasing the embodied energy count by 4,000 megajoule per kilogram per kilo you bring to GEO. And this is a Young's modulus chart of just such the materials that we could select at GEO. Next slide. If we now do a scenario 2, where we fly with one Starship from Earth to the Moon, mine on the lunar south pole, and then go to the geosynchronous orbit customer location, we would have 45 tons of materials that we could actually level. And this would be an addition of an energy count of 1,500 megajoule per kilogram in terms of the embodied energy over the Young's modulus. If we go to the next slide. If we now look at the scenario 3, where we go to Earth, a near-Earth asteroids using ISRU and then to GEO, we could level one Starship to bring 100 tons of materials to GEO. And this would have an embodied energy addition of 760 megajoule per kilo. So here in this scenario, using just one Starship, because if we have a whole space economy, it would be different. But just leveling one Starship and going out of the gravity well of Earth, which is the highest addition of the embodied energy, of course, in this shipping scenario, the asteroids would have, near-Earth asteroids would have the best approach in terms of being actually the cheapest in terms of embodied energy. If you go to the next slide, however, the near-Earth asteroids do not show up in the accessible mining volume for terrestrial bodies because there's a small volume. And I just want to make sure here to make clear, on Earth, 5% of the whole energy we consume is used for crushing rock. So the essential consideration is, in our ISRU efforts, building things in space, regolith runs the show. So space weathering is great because regolith is already crushed. And there is not so much regolith, but we can still make it work. So next slide. Next. So how could we actually, without beneficiation or a lot of beneficiation, kind of fuse these regoliths that we found out have very good low embodied energy? So we could use sintering, melting, powder pressing, powder agglomeration, aggregate bonding, chemical fusion, freezing, right? And then we have all these subcategories of studies that have already been done. If you go to the next slide. One more. Let's look more in detail in the scenario 2. So Earth to Moon using ISRU, and then next slide. From the lunar materials, we could produce a glass or molten basalt. We could use lunar rocks right away. We could use make bricks, sintering. We could actually use the ice from the lunar south pole also as a structural material for these geo satellites. Okay, this is my proposal here. Think of we're building space structures using really raw regolith materials. If you go to the next slide. And then for the asteroid materials, I need one back, please. For the asteroid materials, okay, here. We have a lot more material choices because asteroid materials are somewhat differentiated. And this is why we actually would want to go to these asteroids, because there's phyllosilicates on there. And these phyllosilicates of the C-type asteroids, they hold the water, why we would go to near-Earth asteroids to mine fuel anyway. So the material choices for near-Earth asteroids are quite a bit more diverse. We could produce porcelain from asteroid materials. Again, glass, stone, brick, ice, terracotta. And we could actually use these asteroid materials to produce adobe clay brick. So if we go to the next slide. What my proposal here is, why don't we think about a space clay economy in which we go to asteroids, C-type asteroids, we mine for the water. This is something that's been discussed for a while, of course, but we not only use the water for fuel, but also bring, for example, to GEO, raw clay minerals. And just to give you an impression how much of these C-type asteroids could have clay minerals, you see on the right in the red slide. So this is a thin section from Ruigo asteroid, and this material consists to 88 volume% of these clays I've just been talking about. In this case, is saponite clay a major consistence component. So if you go to the next slide, Kevin Cannon here at Mines and me, we're working on this, and here is an image from Kevin on the left, where you actually see the phyllosilicate volume over the total material volume of these terrestrial bodies. And we have the C-type main belt asteroids that have an amazingly high phyllosilicate volume. Then on Mars, the crust has, let's say, 15 to 30% phyllosilicates. Ceres, we have some. And then this small dot on the bottom in the C-type near-Earth asteroids would be the phyllosilicate volume on these near-Earth asteroids that I'm talking about. Actually, what I'm doing here at Mines currently is seeing if we can also turn the lunar regolith into phyllosilicates by leaching. Well, I don't want to go too much into detail, but the lunar material would also be a prime candidate to produce these nano sheet clay structures that could be very helpful in actually producing satellites. If you go to the next slide. So my research group at TU Berlin has been focusing on using these raw materials as is for Mars and turning them into adobe and ceramic materials by sintering. Next slide. And these are very useful in terms of, here we have Ashby charts again, in terms of how much material you would need to ship to the Martian surface. And if you go here in the red, you see work from my group, which is on the very low end of materials you would need to ship for the Martian surface. If you go to the next slide. We are currently producing novel clay simulants for Mars, mixing the MGS-1 from Exolith Lab, developed by Kevin Cannon, with clays from the Clay Mineral Society to produce adobe. And my PhD student, Sarah Santos, who will do her PhD on this line of work, is in the audience. So if you want to talk to her about this, you're very welcome. What we found is that these different clays, now talking about Mars clay materials, have a very good green body adobe compressive strength that surpasses adobe compressive strength on Earth, actually. And if you go to the next slide, this could well be used. Sorry, this is an old slide. So if you go one further, to produce, for example, a clay Mars house. But what I wanted to tell you here is that we don't need to think of this clay and sintered ceramics necessarily in terms of just being good for housing, what we do on Earth. Because of the stresses in geosynchronous orbit of these structures being very low, because they don't need to kind of be carried on a rocket, to geosynchronous orbit, we could actually think about something as non-space age as mud to build satellite structures. And this is what I wanted to talk to you about. Thank you so much.
Thank you so much, David. And you can, of course, ask him questions online. 2 more talks before lunch, so we'll power through. Our next talk is Paul Zabel's talk. He is from DLR, and he leads projects on space resource utilization.
Institute of Space Systems in Bremen in northern Germany. And basically, my whole team is here. So we are a team of 2 PhD candidates, 4 students at the moment, and myself. And I will give you an overview about all the different activities that we do in my group. So we have 4 big areas that we work on. So the first one is system analysis, modeling, simulations, which comes from, how our department is called. And then the more ISRO-focused areas are regolith beneficiation and utilization, in situ propellant consumables production, and also looking into how we can establish a shared infrastructure between ISRU and life support systems. In the first topic area, so system analysis, modeling, simulation, we focused in the past 2 years on feasibility studies and concept analysis. And right now we have one concept study that a student of mine is doing, who looks into how much mass it would cost to extract oxygen on at different locations on the moon, and how to export it to different orbits, so either to the Lunar Gateway or to LEO, to GEO, to Lagrange points, and how those different locations where you produce the oxygen and where you want to have it figure into the costs or the mass costs that you need to export the oxygen as a propellant component. We hope that we can get the results published this year, but it's still quite complicated ongoing work with a lot of different criteria going into that concept study. More hardware-focused project is in the area of regolith beneficiation and utilization. We have now fully functional regolith beneficiation test stand, which is shown on the right. It's roughly 2 meters high, so we combine different beneficiation steps in a free-fall system. We feed the regolith simulant at the top. We run it through a 200 micrometer vibratory sifter to get rid of all the larger particles. And the finer grain sizes then go through a magnetic separator, which separates the magnetic, non-magnetic particles. And then further on, parts of those particles go through a tribocharging and electrostatic separation at the bottom. My student Kunal from the TU Berlin is currently performing the last set of experiments. And he has a poster in the lobby already showing some results. And we focus here on enriching ilmenite, as previous speakers already said. It's a very nice target mineral, but the concentrations in the regolith is very low to really effectively use it as a source material. And we hope that we can really enrich the ilmenite and our feedstock material to a large degree to improve the efficiency of oxygen and metal production. In our second field, the area of in situ propellant consumables production, we focus on water extraction. Here we also focus a bit more on water extraction on the moon. We are now preparing laboratory scale experiments, as you can see here in a concept drawing, with icy regolith simulant mixtures and to evaluating different parameters like heating powers, etc., how to effectively extract water from the regolith simulant, icy regolith simulant, to get some ideas how it could be on the moon. The problem that we have here is basically the state and condition of water ice on the moon is not really known yet, so we are also looking forward to get more data from the Viper mission, for example. But we do, with the assumptions that we have now, we can do quite nice experiments. And we have 2 posters in that area. One is from my PhD candidate, Luca, who focuses more on the water extraction part. And then we also have a poster about the cold trap water capturing system, which is done by one of our students, by Chris. If you have more detailed questions about those types of research that we are doing here, I really invite you to go to our process and talk to my students and PhD candidates. In the area of combining ISRU with life supports in a kind of shared infrastructure, we focus on water, hydrogen, oxygen infrastructure because I think water is really a very nice, versatile resource that you can convert to hydrogen, oxygen, and also backwards. Right now, here we focus on how we can purify water that we have extracted on the lunar surface. We assume there will be lots of contaminants and volatiles in there. Also for that, data points are very little. There's basically just the one data point from the ELCRIS mission. So we also hope that we have some more data in the coming years that help us to refine the processes. But nevertheless, we start with that already. And we try to bring in here the knowledge that is used in life support systems for water purification. You have to imagine on the space stations, especially the ISS, water purification is done for many decades. And there are technologies existing with a high TRL, but they were never really tested with water that might be contaminated with lunar volatiles. So we kind of want to merge that into an experimental setup to combine those processes that are already very well known for life support and try to see if they can also be used to purify contaminated lunar water. And here again, we have a poster by my student Victoria and my PhD candidate Rike. And we are almost finished with setting up the experiment that is shown here in the flow chart. I didn't have a real photo from the laboratory. And we have also done, or Rike has done, together with Victoria, experiments on dissolving regolith in water to see what type of ions and minerals, etc., contaminants can come out if you put regolith into liquid water, just to get an idea of what could happen if you extract water from lunar icy regolith. All the previous slides showed basically the activities that we do with DLR internal funding in my research group. But we also have a larger project, which is called LUVEX, which we do with 5 more European partners, which is funded by the European Union Horizon Europe Framework Program. It's a 24-month project. We are already in the 6th month, so it's a quite fast-pacing project type. And we work together with the Technical University in Braunschweig in Germany, with Liquifer Systems Group from Austria, with Thales Alenia Space in Torino in Italy, and with the Wrocław University of Science and Technology in Poland, and also with Scanway, a company from Poland. And what we do in LUVEX is we integrate a complete water extraction and purification process chain into one experimental setup. So we want to start with a water ice regolith, so icy regolith simulant. Then we go through the extraction, capturing, liquefaction, purification, and storage. And we want to do that in a meaningful size. What that means, it's hard to say. We still try to figure out how much sample volume we can fit into our experimental setup. We will implement this test setup by having the water extraction capturing part sitting inside a thermal vacuum chamber and having the purification and storage part sitting outside of the thermal vacuum chamber. And if you want to see more about that project, we also have a very nice website. And we just now in between the preliminary design review and the critical design review, so by summer this year, we hope that we have a very solid experimental design that we can then start building in the coming months. And the plan is that we start with the experiments February, March next year. So depending on when Space Resources Week 2024 is going to be, I might be able to show the first results from that project. So thank you very much. And if you have questions, just come to me, come to my team, and we can have a chat.
Thank you very much indeed. Our last talk before lunchtime. Please welcome to the stage to talk about Euro to Moon. It's Bertrand Baratte, and it's going to be a talk entitled Leveraging Lunar Resources Exploration to Foster International Collaboration and Benefit Sustainability in Space and Earth.
Okay, thanks very much, Lisa. So I think I have a big mission here because I'm the last before lunch, so I'll try to be efficient and a good appetizer. I'm Bertrand Baratte. I'm director of the space market for the Air Liquide company, and aside, I'm also general secretary of Euro to Moon. In a nutshell, what is Euro to Moon? That's an industry-led association that was created 1 year ago in Luxembourg to bring together complementary partner from Earth and space industry, but also new space startup and research to foster the implementation of space resources value chain, and as you all said from this morning, for the benefit of sustainability in space, but also for the benefit of international collaboration. So today, the partner of the association are the following. We have Airbus Defence and Space, Air Liquide and iSpace that were co-founder. We have ESRIC that was the first effective member from the beginning. And for the last 6 months, we have Spartan Space that is developing a portable, inflatable habitat. CEA, Commissariat à l'Énergie Atomique, that is a French research center on nuclear energy. Arthur D. Little, that is an international consulting company on strategy. And ANRT, Association Nationale de la Recherche et de la Technologie, which is basically an association bridging research and earth industry in France. And we have as honorary member and senior advisor Jean-Jacques Dordain, that you all know here, and that is really trusting in this endeavor. This is happening in a context that is absolutely amazing. For the last 20 years, we are observing a major disruption that are ever accelerating space sector. So first, of course, we have this revolution of big data. That is just the beginning. Then we have this revolution of reusability that is fully democratizing the access to space, thanks to SpaceX. And today we have this revolution of mega constellation era. And I think human terrestrian want more and more. And this is clearly highlighting a paradox that is a paradox between space and sustainability. On one side, space is getting omnipresent in our day-to-day life, clearly serving sustainability objective on Earth. And on the other side, space operations are starting to become unsustainable, jeopardized by the ever-increasing space debris that could one day lead to many difficulties. So clearly, we have no choice. Our next leap is to open a new era of space, a so-called sustainability in space era. And as all you said this morning, space resources will be the cornerstone of all this. But now there is one major question. As space resources are a common good, and as a celestial body, and certainly the moon will be the cradle of our extraterrestrial life, do we want this to be a competition between Artemis and CLEP, or do we want this to be a universal collaboration? And this would require major third party to step into it, to jump into that endeavor with 2 feet, and to bring transversal contribution to be able to bridge this initiative and to make it a global one. So if we look at this very simplified sustainability in space macro roadmap that is under development by Artemis and CLEP, clearly Europe has many talents to join this endeavor in its space, but also in its non-space ecosystem. And especially, if we look at space resources, those will be absolutely transversal, allowing to serve the purpose of long-duration transportation, lunar night survival, infrastructure, life support, but also it will benefit every science experiment. It will benefit the rise of the cislunar economy. And last but not least, it will benefit international collaboration. So that's why we've created this association, Euro2Moon, with one goal or one reason for purpose. This is to leverage lunar resources to foster European leadership and collaboration in benefit of sustainability in space and on Earth. And our strategic vision, mid-term, long-term, would be to position the European industry with 2 feet as a leader of the rising cislunar economy by creating a strong industrial ecosystem based on developing an ambitious ISRU vision. Once said that, just with a bit more detail, the short-term objective would be clearly to create this platform, this strong European industrial ecosystem, to explore these resources in a sustainable and commercial way, and to be representative of the whole value chain, because it's not worth having the best technology ever if all the ecosystem is not prepared to run it as a service. The second objective would be, of course, to create this platform of discussion, to enhance each of us space strategy, and to build altogether a common industrial roadmap and to perform gap analysis. And of course, the association will represent its members of the space and the non-space industry to promote space resources as a lever of an enabler of sustainability in space and on Earth, which is not obvious. If you get out of this room and you speak about space resources and sustainability, the link is not obvious in the streets. So to become a member, first you need to share these ideas, to have a vision and an ambition with regard to cislunar economy and the development of space resources. And the idea is to start with representative of European Commission or ESA state members, and of course from space industry, non-space industry, new space SME, and research. The advantage and the interest of this endeavor is to foster interaction, but also coordination in between the members on their development efforts. And the best way to organize and to accelerate the rise of new commercial usage would be to organize on-the-ground demonstration by putting the technology and the services that are existing on the table all together and try and start working on the interface, start working on the architecture, and hopefully to accelerate the rise of services such as oxygen and power for habitat, hydrogen for surface mobility, energy storage for lunar night survival, and of course propellant production for spacecraft refueling. And in that prospect, as far as we'll be able to find a moon field or play field, and of course a bit of sponsorship, all the players of this association would be ready and happy to bring their equipment and to operate them together towards end-to-end solution. The first, of course, idea would be to demonstrate the production of oxygen, drops, but also power, and certainly metal or equipment for structures from existing equipment. Illustrated in figures, so this is a demonstration we organized quick and dirty last year during the ESA and ESRIC challenge, thanks for that, in the Rock Hall in Luxembourg. So basically what we did, we brought the equipment that was existing on the table. So you can see on the picture the regolith extractor from Airbus Defence and Space, ROXY. You can see the functional rover from iSpace. On the top of the rover, there was oxygen and hydrogen cylinder, and then you can see on the back the habitat of Spartan Space, the inflatable habitat of Spartan Space that were mounted on the lander of ESA. And clearly, on the habitat, there was a fuel cell system also to provide energy. So this was mock-up, and the idea, of course, is to grow up this approach to be able to deliver services. So how we are organized? We are organized with 5 working groups. One working group on communication, let know our initiative and to grow the momentum. We'll be present in different events this year. Then we have a business and market working group to develop an understanding of the market demand, which is clearly the main question each time we want to invest in the subject. Then we have 2 working groups with regard to value chain, oxygen, hydrogen, water, but also power value chain, to design demonstration proposals, but also to assess the value chain, define the gaps, and will, in that prospect, propose a space resources hackathon during SpaceCon at the end of the year. And last but not least, we have a sustainability working group to define the right KPIs to show the link in between space resources and sustainability. So I'm finished. If you want to join us, as Oscar Wilde is saying, feel free, because finally the main risk you will take is to land among the stars. So we have a booth there, so feel free to come and join us. Thanks so much.